In this video, we're going to look at how we can find a vector between 2 points. So here I've drawn 2 points on a Cartesian plane. The coordinates of the first point are 3, 1, and the coordinates of the second point are 10, 7. So the points are labeled A and B, and I want to actually determine or draw the vector from A to B. So based on that notation, again, this is clear that the vector originates at A and terminates at B. In order to determine an algebraic representation for this vector, what I'm going to need to do is examine the horizontal and vertical components of this vector. Now, if I look at the components, it's again very easy to do this by drawing a right-angled triangle with the vector as the triangle's hypotenuse. And then if you look at the length of the bottom of this triangle, or the base of this triangle, that represents the horizontal component of the vector. If you look at the height of this triangle, that represents the vertical component of the vector. And so I can see here in my x values, I start at an x value of 3, and I go over to an x value of 10. So that means I've moved 7 units to the right. And if I look at the height of the triangle, I start at a y value of 1, and I end at a y value of 7. So that means that I've gone up 6 units. So as far as the components then for this vector AB, I could write that as 7, 6. So that's representing the vector in column vector form. I could also represent it with my basis vectors, and it would be 7i plus 6j. Now I was able to determine that by drawing the vector and mapping out the components. But if you think about it intuitively, and the way I described it was based on the x values and y values of the point and the differences between them, where I started and where I ended, and how far was traveled in between on the x values and how far was traveled in between on the y values. And that's because if I wanted to find a vector between 2 points, any 2 points, and let's call the points A with general coordinates A1 and A2, so those are its x and y values, and the second point then can be B, where its x value is b1 and its y value is b2. In general, then, the vector between those 2 points is going to have the components b1 minus a1 as its x component and b2 minus a2 as its y component. So essentially what we're doing there is we're taking the larger of the two, subtracting the smaller of the two, to establish the distance between them. b1 minus a1 is the distance between the x values, b2 minus a2 is the distance between the y values, and those give us our horizontal and vertical components for the vectors. So let's look at an example strictly through an algebraic lens. So here I've just got 2 new points, their coordinates are given, I have x values and y values, and I want to find the vector AB. So again, I'm taking the x values and subtracting them, starting with the point where it terminates and its x value, and then I'm subtracting the x value of the point that it originates at. And then I'm going to do the same thing for the y values. So the y value of the point where it terminates, and subtract the y value of the point where it originates. And then I just have to evaluate here, and I get the components of this vector are -5 and -4. So you can see, algebraically, it's very, very easy to find a vector between any 2 points. So what can we do then with this information about how to find a vector between points? Well, what it's actually really useful for is helping us to identify properties of shapes that we know are composed of certain vectors. So here I've given 4 points. These 4 points can be the 4 vertices of a quadrilateral, so some 4-sided figure. And they go in order A, B, C, D in a clockwise fashion around the figure. And so right now I've labeled those points, but I don't actually know what kind of quadrilateral this is. If I had grid paper, I might be able to graph it and then get a clearer sense. But given that I don't right now, I need some sort of way that I can classify this quadrilateral. And there's lots of different classifications that it could fall under. It could be a parallelogram. It could be, more specifically, a rectangle. More specifically than that, it could be something like a rhombus or a square. In fact, it could even be a trapezoid. So in order to classify these shapes, I need to determine some properties about the shape in question. I need to know, are opposite sides parallel, and are their magnitudes equivalent? That's going to help me actually narrow down whether it's a parallelogram or a rectangle or a rhombus or a square or a trapezoid, based on looking at things related to those points and the vectors that connect them. It'll make it easier to identify what kind of quadrilateral it is. So what I'm going to need to do to classify this shape is actually find the vectors between adjacent points. And I'm going to want to pick them so that they go in the same direction. So I'm going to need to find vector AB, and I'm going to need to find vector DC. I will also need to find vector BC and vector AD. So I've paired those up because those are opposite sides. AB and DC are opposite one another, and those vectors would be going in the same direction. And similarly, BC and AD are opposite one another and going in the same direction. So if I determine the components of these vectors, I should then be able to compare them to get a sense of what kind of shape this is. So I'll find the components of vector AB. That's going to be 3 minus 2 and 5 minus 1. So I get my components as 1, 4. And then for DC, I'll do the same thing. So I'll have 9 minus 8 and 3 minus negative 1, which gets me 1, 4 as well. For BC, I will have 9 minus 3 and 3 minus 5. So the components for that vector are 6 and negative 2. And then I'll calculate for vector AD. I have 8 minus 2 and negative 1 minus 1. So I end up with, again, 6 and negative 2. So now that I've found these vectors, I can actually look at them and say, if vector AB is the same as DC, and vector BC is the same as AD, I am now able to say with certainty that those 4 points, they make a parallelogram, but that parallelogram could technically be a rectangle. It could be still a rhombus, it could be a square. It's definitely not a trapezoid, though. So because opposite sides have vectors that are equal to each other, I know that they're parallel. They're going in the same direction. Trapezoid, though, has only one set of parallel sides. And since both sets of sides, of opposite sides, match up, they're parallel with each other, I know that it can't be a trapezoid. So I've ruled that one out. In terms of narrowing it down a little bit more, it might help to figure out the length of those sides. So what if all the sides are the same length? Do they have the same magnitude? Because then that would narrow it down to a rhombus and a square. Whereas if they're not the same magnitude, I know that it's either just a parallelogram or perhaps more specifically, it's a rectangle. So let's find the magnitude of AB, recognizing that that's also the magnitude of DC. And then we can find the magnitude of BC and recognize that that's also the magnitude of AD. So the magnitude of AB is going to be equal to the square root of 1 squared plus 4 squared, which is equal to root 17. And the magnitude of BC is going to be equal to the square root of 6 squared plus negative 2 squared. And so that's the square root of 40. So I can see that one set of sides is clearly longer than the other. BC and AD are root 40. That's a much larger length than AB and DC. So I can tell at this point, because the lengths don't match up, definitely ruled out a square and a rhombus. Now, in order to verify whether it's a parallelogram or a rectangle, I would need to know if these vectors are meeting at right angles. And so here's the trick to identifying whether they meet at right angles. If I have a vector 1, 4, so I go to the right 1 unit and up 4 units, in order to meet at a right angle, a vector would have to actually take the components, flip them, and make one of them negative. So if I was to head right 4 and down 1, and draw that vector. So this vector here is meeting with this one at a right angle. So if the components of the vectors are swapped and one of them is changed to be negative, then I know they're meeting at a right angle. That should seem familiar to you because it's the same idea as with slopes. Finding the negative reciprocal of a slope is giving you the perpendicular slope. It's the same mechanics that are at play here. And so if my vectors actually had components that were flipped and one of them had changed signs, I would know that they were perpendicular. But if I look at my vectors, one of them is the vector 1, 4, the other one is the vector 6 and -2. And so because I know that those aren't then just a matter of swapping components and changing the sign, I know that AB is not perpendicular to vector BC, so that rules out a rectangle. There's no right angles there, so I can say with absolute certainty that this is a parallelogram with no other specific classification to it. So opposite sides are parallel, opposite sides are the same length, but that's all I can say with certainty, so I can only classify this one as a parallelogram. But based on those checks, seeing whether the vectors match up, seeing whether the magnitudes match up, and checking to see if they meet at right angles, can allow me to classify any grouping of 4 points as forming any number of quadrilaterals: parallelogram, rectangle, rhombus, square, or trapezoid. And so that's one of many, many useful features of being able to find a vector between 2 points, is being able to analyze different geometries in a different way.